At this very moment, you are sitting on a huge rock called Earth. It weighs about 6 sextillion tons. According to our everyday experience, heavy objects should fall. If you let go of a stone, it will crash to the ground. So why doesn't the Earth, such an incredibly heavy super rock, fall, even though it is suspended in empty space with nothing supporting it beneath? What is actually holding it up? The answer is both simple and mind-bending. The Earth has actually been falling the whole time. It has never stopped. It's just that the way it falls is filled with a kind of cosmic artistry. Today, let's break down this ultimate mystery of falling. First, we need to correct a concept that human intuition often misleads us about. What is down? On the surface of the Earth, we think down means the direction beneath our feet. That's because Earth's gravity pulls us toward its center. For someone living at the North Pole, down points toward the center of the Earth. For someone at the South Pole, down also points toward the center of the Earth. So people at the South Pole are not hanging upside down. Everyone is standing with their feet toward the center of gravity. In essence, down is simply the direction where gravity is strongest. When we go into space, Earth's gravity still exists. But on a larger scale, the boss of the solar system is the Sun. The Sun contains 99.86% of the total mass of the solar system. Its gravitational field is like a massive whirlpool that dominates everything around it. So within the solar system, the true down is actually the direction toward the Sun. If the Earth were really just hanging motionless in space, then the answer would be quite cruel. It truly would fall. It would plunge straight toward the Sun, like an apple released from your hand, diving into that abyss and eventually being swallowed by the Sun's scorching surface. So why hasn't that happened? Because the Earth is doing something desperately important. It's trying to escape. More than 300 years ago, Newton, in his book Philosophiae Naturalis Principia Mathematica, drew a famous sketch that perfectly explained why the moon doesn't fall down. Imagine this. You are standing on a very tall mountain that rises beyond the atmosphere, and you set up a cannon. For the first shot, you gently fire a cannonball. The ball flies forward a short distance, traces a parabolic arc under the influence of gravity, and falls to the foot of the mountain. For the second shot, you fire the cannonball so fast, about 7.9 kilometers per second. Now a miracle happens. The cannonball is still falling. It still wants to drop toward the ground. But the Earth is round. When the cannonball travels far enough forward, the amount the Earth's surface curves downward is exactly the same as the amount the cannonball falls. In other words, for every meter the cannonball drops, the ground also curves downward by 1 meter because of the Earth's curvature. So the cannonball keeps falling forever, but it always misses the ground. This state is called orbit, what we commonly refer to as orbital flight. The relationship between the Earth and the Sun is just like this cannonball. The Earth is not floating in space, it is actually desperately falling toward the Sun. But because it is also racing sideways at an extremely high speed, so that every time it falls, it perfectly misses the surface of the Sun. To maintain this state of falling forever without ever hitting the bottom, the Earth pays a huge price, and that price is speed. The Earth's average speed along its orbit is as high as 29.78 kilometers per second. This is the Earth's tangential velocity, and it is part of a cosmic tug-of-war that has lasted for 4.6 billion years. On one side is the Sun's gravity, like an invisible rope, pulling the Earth relentlessly downward, that is, toward the center of the Sun. On the other side is the Earth's inertia, trying to fly off along a tangent, to escape the solar system and shoot out into the dark depths of the universe. These two forces have reached a perfect balance over the past 4.6 billion years. If the Earth were to slow down, gravity would win, and the Earth would spiral into the Sun. If the Earth were to go much faster, inertia would win, and the Earth would break free from the Sun's chains and become a wandering planet. So the reason the Earth doesn't fall is because it's running too fast. You might ask, if the Earth has been racing along, why hasn't it slowed down after 4.6 billion years? On Earth, when you throw a ball, it soon stops because of air resistance. But the nature of space is vacuum. As the Earth travels through space, there is almost no friction. There are no air molecules to collide with the Earth, no wind resistance to drain its kinetic energy. According to the law of conservation of momentum, the enormous initial speed the Earth gained at its birth has been preserved almost entirely without any loss. This is true inertial drift. Unless a massive asteroid impact occurs or humans intervene in some extreme way, the Earth will continue to glide like this, unpowered, for billions of years. Newton's explanation was already perfect enough to send humans to the moon. But in the 20th century, Einstein came along and said something even more astonishing. In fact, even the concept of force isn't fundamentally necessary. From the perspective of general relativity, The Earth doesn't actually feel a force pulling it toward the Sun. Gravity, at its core, is the curvature of spacetime. Imagine a huge rubber sheet suspended in the air. If you place a 100-kilogram iron ball in the center, the sheet will sag, forming a deep depression. Now, if you roll a glass marble from the edge, it will naturally fall into the pit. But if you give the marble some sideways speed, it will circle around along the inner wall of the depression. In Einstein's view, the Earth is actually moving in a straight line. It follows the so-called shortest path through four-dimensional spacetime. It only appears to orbit the Sun in our three-dimensional perspective because the Sun's massive weight bends the space around it. The Earth thinks it is moving straight, but in our macroscopic view, it is tracing a curved path. So the Earth isn't floating in empty space. It is trapped in the spacetime pit created by the Sun, running along the walls of that pit. It doesn't fall in because its rapid motion generates a centrifugal effect that counteracts the pull toward the pit's bottom. Don't be fooled by the illusion of floating. Our Earth isn't resting peacefully anywhere. We are sitting on a giant cosmic spaceship, hurtling past the Sun, a massive nuclear fireball, at tens of thousands of kilometers per hour, performing a breathtaking drift around it. This is an extremely delicate balance and an ultimate expression of cosmic beauty. If the Earth's speed were even slightly slower, or the Sun's gravity slightly stronger, the story of humanity would have already ended. What we call peace and stability is really just the result of us racing through space at incredible speed. Thanks for watching and for taking this incredible journey through space with us. If you enjoyed the ride, don't forget to like and subscribe. We'll see you in the next video. Until then, keep looking up.